So coming to the orthogonal complement. So another definition we can call orthogonal complement. So what do you mean by orthogonal complement is that you have a subspace V and all the vectors that come under this V, V1, V2, V and any number of vectors Vk that span R raised to n are called orthogonal complement of V if all the vectors are orthogonal. If all the vectors are orthogonal, then we call that as an orthogonal complement of V. It is denoted by V, and that is a perpendicular symbol indicating that all vectors in V are orthogonal. So V perpendicular. So that is the definition. So you know that the null space is orthogonal to the complement of row space. So the null space is the orthogonal to the complement of row space, or you can say the null space is orthogonal to the row space. So you can write it as whole of your null space is orthogonal. Whole of the null space is orthogonal. So you can say column space is a complement of, that is orthogonal complement of column space is equal to null space, or even we can write it as vice versa. Whole of the columns are orthogonal to the null space. So hence you can say the null space orthogonal complement of the null space is equal to the column space, because all the vectors of null space are orthogonal to column, or all the vectors of columns are also orthogonal to the null space. Hence you can call, when all the vectors are orthogonal, then you can call it as an orthogonal complement of that vector. So here the as you know, this already you know this, the dimension of row space and the dimension of null space should be equal to the number of columns. So you can have here. So and then one more according to the dimension of row space and dimension of null space, even you know that the left null space and the column space are orthogonal complement, and the dimension of column space and the left null space will be the number of rows. So these are the properties for from the four fundamental spaces also. You know the dimension of column and left null space are leads to a number of rows. So hence it is, because the column space here we will have it as m minus r, and here the column space is a r, and r gets cancelled. You are left out with the m, that is the number of rows. So all this already have studied in the four fundamental subspaces. So this also I have explained you already. That is, you can have W and V are orthogonal to each other. These two are orthogonal, and the third vector is not orthogonal. So you cannot say that whole of they are orthogonal complements, because R cube, if I am taking in terms of axis, you have W, V, and if you take it as U is not a complement to W and V. So you have only two axes are orthogonal. So you cannot say it as whole orthogonal complement. Here you can see, if I take all the three spaces are three in a plane, you have this plane perpendicular to W. Line W, this is line W, and this is your V, the plane, and W is perpendicular to the plane V. So W is the orthogonal complement of V, but V is not orthogonal complement of W, because every line in this plane is not orthogonal to this W. So W is orthogonal complement of V. So that is one example of orthogonal complement. So coming to the matrix and the subspaces. When you have orthogonal vectors can be represented in terms of matrices, and you can have a subspaces representing in terms of matrix, and depends on if I am taking an axis of two dimension, as you know that I can represent it as 1 0 and 0 1. Similarly 3 I can represent it as 1 0 0 0 1 0 and 0 0 1. So here we can have V and W be orthogonal without being complements. So it's not necessary that they have to be complements. So some vectors of V and W can be orthogonal without being complements. So the line V spanned by, here example, if you have a V spanned by 0, 1, 0, is orthogonal to the line W spanned by 0, 0, 0, 1. So both are orthogonal, but V is not in W per, space. That is, the W is not an orthogonal complement to V. So that itself that I showed you in the previous figure. So here the same thing I'm showing you. I'm talking in terms of this figure, above figure. So that I have explained you. Coming to, so here you can have one more thing. So W, if W is equals to V perpendicular, then V is equals to W perpendicular, and dimension V and dimension W should be equal to N. So if W also is perpendicular to V perpendicular, then this goes to. Then, and one more thing is that perpendicular to V, and taking again the perpendicular of that V, that is orthogonal complement to the orthogonal complement is equals to V. That is projecting the vector twice. So that becomes, that is nothing but projecting at 90 degrees twice. So it becomes equals to the vector orthogonal complement. And here you have the whole space in R raised to n is being decomposed into two perpendicular parts. As you have seen in figure 1, you can have only, if you have R raised to n, I cannot have more number of vectors in terms of axis. Only I can have these two vectors as two perpendicular parts. I cannot have a third axis, fourth axis being perpendicular to all each other, because I can have only one, two, that is vectors in terms of minus and plus. They will be in the complements. So you can have the orthogonal parts, we can split them into V and W. So your X, in terms of matrix if I am talking, so that is AX you will be having, and AX equals to B is our solution. So this part X in terms of orthogonality, when we are talking about orthogonal vectors, this can be split into V plus W. That is V plus W. So V is projection into the subspace in V, and orthogonal complement W is the projection of X onto W. So here you have V, you have two vectors. You can see V is just a vector in subspace V, and W being the orthogonal complement of projection of X. So it is nothing but null space and row space you can have. That is, you have a null space and a row space. So X can be differentiated as V plus W means something, but X is split into XR and XN. So V is projection onto the subspace and orthogonal complement of W. So it has to be either null space and row space, or the column space and the left null space. So we are taking only the row space and the null space. So you can divide the X into row space and the null space. Okay. Your X n goes to what? Null space, and every other vector Ax goes to the column space, and that column space itself you can call it as a row space. Here